guys, let's go over this. Okay, so all along I've been trying to convince you to learn your functional groups so you can identify them in reactions and predict what's going to happen to those functional groups in the reaction. So in the starting material we have two functional groups. We have an ester and we have a ketone. Right, so two carbonyl functional groups. They're going to have more or less the same basic reactivity, right? Both are going to be electrophilic at carbon, right? Both are going to be somewhat basic at the carbonyl oxygen, right? But we've learned over the past two classes that an ester and a ketone are going to react differently with sodium borohydride, right? So how is that difference manifested? What's going to happen if we add sodium borohydride to a molecule that has an ester and a ketone?
It's going to interact with the ketone.
It's going to interact with the more electrophilic of the two functional groups, right? It's going to interact with the ketone. Right, so we've learned that sodium borohydride is a chemoselective reducing agent. Right? And what this means is that in the presence of multiple functional groups that have the same general chemical reactivity, it's going to select for one type of that functional group over another type of functional group. Right? So this is sodium borohydride. It's going to be selective for ketones and aldehydes, right? Which are carbonyl functional groups, but is not able to reduce or react with esters and amides, right? Which are also carbonyl functional groups. Okay, so it's chemoselective, right? It's selecting for the specific type of chemical properties that it can react with. Okay, so mechanistically what's going to happen is it's going to ignore the ester, react with the ketone. Deliver the hydride to the carbonyl carbon of the ketone, break the carbon-oxygen pi bond. And then if we're doing this in an alcoholic solvent, like isopropanol, ethanol, N-propanol, right, some regular alcohol solvent, then that alcohol will lend a proton to our product. Right, and that's going to be the product after the first step. Okay, so you can see when I draw these reagents up here, I drew numbers before them. Whenever you represent reagents that way, even though they're all above the same arrow, what this means is that you're adding the first set of reagents, letting that reaction go to completion, right? Maybe working up the reaction, maybe not, right? But letting a reaction happen fully, and then adding a second set of reagents and letting that reaction happen fully, right? So we're not throwing everything in there at the same time. We're adding the first set of reagents, letting the reaction occur, adding the second set of reagents, and letting the reaction occur. So after the first step, the sodium borohydride reduction, this is what our product is going to look like. Right? You can see that the ester is still intact. And we've created a new functional group. So what's that new functional group?
Alcohol.
Great, an alcohol. Okay, so now we have an ester and an alcohol, and we're treating those, we're submitting those to acidic conditions. Catalytic acid. What type of reaction is this?
It's a reduction.
Not a reduction. Sorry.
That's cool.
Add an alcohol to an ester. What if it was adding an alcohol to a carboxylic acid under acidic conditions? What type of reaction would that be? Do you know that one, Drew?
It's I might have to consult my notes. But
Okay. I didn't need to put you on the spot.
Yeah.
No, it's going to be more than just acid-based reaction.
Fisher errors, esterification.
There you go. Fischer. So when you add an alcohol to an acid, right, you make an ester. Fischer esterification. Okay, so when you're adding an alcohol to an ester, right, this is just a trans-esterification, going from one ester to another ester. That's all we're doing. Right? And so in that case, this is our leaving group. This is the alcohol that's going to be our leaving group. Right? This is the alcohol that's going to become part of the ester. So the first step is going to be protonation. Right? After we protonate, we're going to add to the carbonyl, right? Take the alcohol, add that to the carbonyl. Release this. Right, so we, that's the wrong chart, sorry about that. H plus. Okay, so this is the bond that we just made, right? We're taking this alcohol, adding to the carbonyl, making a new 5-membered ring. Right? Next step is going to be a 2-step proton transfer, so we're going to take the proton off of this oxygen, put it on to the other oxygen that we're using as a leading group. Kicking that leading group out. And then the last step is deprotonation. Questions about this?
Isn't the product a little bit different than the one you have on there?
Yeah, all I've done is I've taken this, flipped it upside down, right, and kind of rotated it around a little bit. Same molecule.
So the
Oh,
isopropyl.
yeah, sorry, that is wrong there. Thank you. questions? Okay, so again, this is why it's important to learn the functional groups, right? Because if you're looking at the starting material and you can identify that there's an ester and a ketone, and you remember sodium borohydride doesn't work on esters, right? Then you could focus on the ketone. Okay, same thing with the second step. If you know that the combination of an alcohol and an ester under acidic conditions is just transesterification, and you can identify those functional groups, right? Then you know what's going to happen. Right? So if you're still struggling with identifying functional groups, that's definitely one thing that you want to practice between now and the end of the semester. Questions before we move on? Okay. So far we've looked at these two reducing agents, right? So sodium borohydride we've seen is good at reducing aldehydes and ketones. Lithium aluminum hydride can reduce aldehydes and ketones in addition to also being able to reduce esters and amides, right? And actually carboxylic acids as well. Okay, this is a third reagent that you're going to learn, a third reducing agent, sodium cyanoborohydride. Right? How does this compare? So we've learned that this is a mild reducing agent. Lithium aluminum hydride is a strong reducing agent. How is sodium cyanoborohydride going to compare to those two?
It would be even more polarized.
Even more polarized. So what does that mean?
Its overall bipolar.
So does that mean it's going to be a stronger hydride donor, a weaker hydride donor? Get a 50-50 shot. Well, so let's think about what makes, what sets this trend in the first place, right? Why is the aluminum hydride a stronger hydride donor than borohydride? Why is it a better nucleophile?
It's more electropositive.
What is more electropositive?
The aluminum.
The aluminum, right? So that is going to make the ALH bond much more polar, right? Giving hydrogen a much bigger partial negative charge than the VH bond, right? Aluminum is more electropositive farther down on the periodic table, okay? And so the difference, electronegativity difference between aluminum and hydride, or hydrogen, is going to be more significant than the difference between boron and hydrogen. So that gives this hydride greater electron density, okay? It makes it more nucleophilic. So that's the difference in reactivity between those two. So we have to think, okay, we have borohydride. The only difference is that we're replacing one of the hydrogens with a nitrile, with a cyano group. So how is that affecting the electron density around the hydrogen? How is that going to affect the nucleophilicity of the hydride? Is that? Yeah? Okay, carbon is slightly more electronegative than hydrogen. What's even a more important element on that group? The nitrogen. Yeah. So the nitrogen, among all of the atoms in this molecule, right? Carbon, 3 hydrogens, and a boron. The nitrogen is going to be the most electronegative element in this molecule, right? So whereas before the electron density was evenly dispersed between all 4 hydrogens, now that electron density, or more of the electron density, is going to be pulled towards nitrogen, right, and away from these hydrogens. Okay, and so as a result, this is going to be a relatively weak hydride donor. All right, we're putting something else on boron to pull electron density away from the nucleophilic hydrogens. So they're not going to be as nucleophilic. Questions about that? Everybody understands that? Okay, so what do we use this for, right? So if we take a ketone or an aldehyde and treat a ketone or an aldehyde with sodium cyanoborohydride, right? Nothing's going to happen. Ketones and aldehydes can be reduced, right, with the regular borohydride, but with sodium cyanoborohydride, no reaction is going to take place. Right? But if we change that up a little bit and we add in an amine, right? Now we're seeing a reaction take place. All right, so in this reaction here, what new bonds were formed? Well, let me ask you this question. This carbonyl carbon in the starting material, where is that carbonyl carbon in the product?
It's now bonded to a hydrogen in the amino group.
Good, right? So it's now bonded to a hydrogen and an amino group, right? So the new bonds that were made in this reaction right? New carbon-hydrogen bond. Right? Where do you think that hydrogen is coming from?
It's coming from the reagent.
Good.
Sodium cyanoborohydride.
Good, right? So this is the hydrogen coming from the sodium cyanoborohydride because that was the carbonyl carbon. Anything new attached to that carbonyl carbon is likely added as a nucleophile, right? Because we know carbonyl carbons are electrophilic, right? So that hydrogen comes from the cyanoborohydride reducing agent, right? And then the other new bond that was formed came from the addition of nitrogen. Okay, so we know if we take an aldehyde and treat it with just sodium cyanoborohydride, we're not going to get any reaction. Right? If we take a ketone and treat it with just sodium cyanoborohydride, are we going to see any reaction? No, right? Ketones are less electrophilic than aldehydes, so if we're not reducing aldehydes with that reducing agent, we're not going to be able to reduce ketones with that reducing agent. Right? And the other reagent that's in here is a primary amine. An acid. Right? So if I take these two functional groups, a ketone and a primary amine, right? And I mix those together under acidic conditions, what's going to happen? What will form? In imine, good, good. Right, and it's an imine that forms in this reaction. Addition of a primary amine to a ketone forms an imine. Addition of a secondary amine to a ketone forms an imine. Right, the mechanism of this starts off with the addition of the amine to the ketone, breaking of the carbon-oxygen pi bond, right? And eventually we're going to get to an intermediate. That looks like this. Right? And then to get to the imine, all we're doing is we're taking a base, plucking this proton off of the nitrogen, and that gets us to the imine. So this is the second to last, or the last intermediate of the reaction, right? Second to last step of the mechanism gets us to this point. Right? This iminium ion that we're making, this iminium intermediate, in terms of electrophilicity, do you think it's more electrophilic, less electrophilic than other things we have in this reaction? How does this compare to, let's say, how does this compare in electrophilicity to an imine? More reactive, less reactive?
It'd be more reactive.
It'd be more reactive, right? So the same idea if we have a ketone versus protonated ketone, right? This is going to be more electrophilic. This is going to be less electrophilic. Right? So having that extra bonding partner and a positive charge, right, makes the surrounding atoms more electron needy. Yeah.
Where did the oxygen disappear when you did that?
So whenever you make an imine, you lose the oxygen as water.
Oh.
Right?
Oh.
So in this reaction, this iminium intermediate is going to be more reactive than the ketone that we're starting with, more electrophilic than the imine that we're making, right? So this is a high energy electrophile. So every once in a while when this is made, right, and before it goes to the imine, before it goes back to the ketone, it's going to meet up with a molecule of the sodium cyanoborohydride. And when it does that, right, now we have a hot enough electrophile to react with this really mild reducing agent. Okay, so whenever it's formed, really reactive, it finds a molecule of the borohydride. Borohydride will deliver a hydride, and that's going to make a secondary amine. Right, so if you're following this according to the functional group, right, we're starting with the ketone and a primary amine. Okay, and And we're making in this reaction a secondary amine. So we're basically adding an alkyl group to the nitrogen, right? Replacing one of the hydrogens. Right? This is a type of reductive amination. This is specifically imine reductive amination. Right? Generally, reductive amination, all it means is the synthesis of imines through a reduction process, through a reduction reaction. Right, so you learned a type of reductive amination the other day. We didn't name it reductive amination, right? But it's a reaction that produces an amine, right? And that amine is produced through the reduction of hydrogen, through the reduction of an amine. Right? We can also take nitriles and reduce them the same way. Right? And now you've learned a third type of reductive amination that involves amines. Synthesis of amines through the reduction of amines. All right, questions about this? Okay, so this yeah, Rachel, go ahead.
You wouldn't need the cyanoborohydride if you were just making it, right?
If you were just making an amine, no, you don't need the, yeah, sodium cyanoborohydride, that's what delivers the hydrogen. That's what reduces the amine, reduces that double bond. Other questions? All right, so we've learned 3 reducing agents, right? Sodium borohydride, lithium aluminum hydride, sodium cyanoborohydride. The first and the last, sodium borohydride and the sodium cyanoborohydride, they're both chemoselective reducing agents, right? They are only interacting or reacting with certain carbonyl compounds that are reactive enough. And that has potential for giving us options when we're synthesizing molecules, right? Because if we have 2 types of carbonyl compounds in a molecule like we saw at the beginning of class, we only want to reduce one, right? Then we can choose the sodium cyanoborohydride to reduce just the ketone, right? Alternatively, people getting anxious, this clock's fast, so yeah, 2 or 3 more minutes. if we want to reduce only the ester in this case. All right, we don't know a hydride reagent that can do this in one step, right? That will leave the more reactive carbonyl alone while reacting with the less reactive carbonyl, right? That's nearly impossible to do this in one step. All right, so, but we have a strategy to accomplish this in multiple steps. All right, and so this is going to tie into what you're doing in lab, right? So this is the reaction that you performed in lab a few weeks ago, right? And this is the product that you're going to be purifying if you haven't already done so over the next week, okay? Whenever we turn that ketone into a ketal, right, we're starting with an electrophilic carbon, and when we're done with that reaction, right? Because we destroy that pi system, that carbon of the ketal is no longer electrophilic. Right? And so we call this a protection, all right? Or a protecting group. We're protecting the ketone. We can put that ketal on, right? Later on, when we're ready, we can take that ketal off, right? So it's kind of like a condom for this molecule. It's preventing that functional group from reacting in a step that we don't want it to react in. Okay, so we protect the ketone, we add our reducing agent that can reduce an ester, right? Ketone is completely unaffected because it has that protecting group on it. We reduce the ester down to the primary alcohol, right? And once that reaction is over, we can take that condom off, right? We can take the protecting group off and return to the ketone. Okay, and so this is the strategy that we would take if we don't have a reagent that's selective for esters over ketones, right? We have to protect the functional group that we don't want to react and then remove that protecting group after the reaction is over. Okay, questions about this? All right, we're going to try to finish up this chapter on Monday, so you can get started on a new chapter when you get back to Thanksgiving. Oh, in terms of the exam, so people have been asking me about this exam. There's a physics exam the week after you get back from Thanksgiving. So there's not going to be an OChem exam that week after Thanksgiving. If it's an in-person exam, it will be the week after. If it's a take-home exam, it'll be sent out sometime that week and you can do it over the week, okay?